Welcome to this second course on model fitting. Last week, we saw that in order to fit a model, if we want to be using the statistical method, we need to have an explicit model of the noise. This will help us find the appropriate score function. What we will see today is how we can use the standard methods, which are about linear models. So let me start with least squares. So this is the default method. In fact, if you ask MATLAB or NumPy to fit a straight line, for example, through a cloud or more sophisticated models, it will usually be the one that is used. So not for bad reasons, as we will see, because it's able, every computation is explicit and it is able to give confidence intervals. So let us discuss what this is exactly. So a least square model has two parts in it. The least square is first what we saw last week. That's the epsilon I is assumed to be homoscedastic. And we have seen last week, this is just a recollection of last result, that this is solved by minimizing the L2 norms, so the square distance, with respect to the unknown parameter beta. And once we have done this, we also have an estimator of the variance as exactly the mean distance here. I mentioned that this method allows us to give confidence intervals. Well, there is this result, which is a bit intimidating, but it says that if we believe in the model, that means if the noise is truly Gaussian, then we have the following result. Beta with an arrow, is the true but unknown parameter that we're trying to estimate. Beta hat is our estimate. This is the solution of the optimization problem. Then approximately, which means essentially when the number of points is large, this is a central limit theorem, very much like we had when we were computing confidence intervals for the mean. So approximately when n is large, we have the following thing. The difference between the true but unknown vectors and the estimated vector, so both of them are multiple coordinates in general, is approximately Gaussian. Now it's a Gaussian vector, which means that we need to specify its mean. So it's zero mean, which is as expected. And the covariance matrix is given by this formula. It is the inverse of the matrix obtained by the cross derivatives of the PDF of the model, of the PDF of the model, exactly, divided, of how the unknown function to be mapped, to be fitted, the cross derivatives of this function with respect to the parameters, divided by 1/sigma square. Right? In reality, we don't know sigma square, so we will apply this approximately by replacing sigma square by its estimation here. Then there is an approximate result that I will mention in a few minutes. But let's see what that means exactly. You may remember that last week we fitted the model of virus expansion by first going into log scale, and then in log scale we had a linear model. We had two parameters, a or log a, and the growth rate alpha. And if we want to use the statistical method, we additionally have the sigma square to fit here. So what does this theorem tell us? Well, it tells us that we should compute this matrix. What is this matrix? Well, it's the matrix of derivatives of the function fi. So what is fi? Fi is the value that we have here when we don't have the noise. So that's the thing we're trying to fit. So fi is equal to log a, which I call a prime, this compressed notation, plus alpha ti. That's a simple case because it's linear. So this theorem says we compute all the cross derivatives. So we compute first the first derivative. With respect to beta 1, what is beta 1? Beta 1 is the first component of the parameter. The parameter, it depends what we call beta 1. Here I call beta 1 alpha and beta 2 a prime. There are multiple ways of parameterizing the problem. They will lead to different calculations, but hopefully to the same final results. So I call alpha the first parameter. I need to take the derivative with respect to alpha, that gives ti. Derivative with respect to beta 2 is 1. And then the cross derivatives. So ka1 will be this square. So if we look at the formula that was given here, we take the sum of the products of the derivatives. So that will give us this formula, 1 over sigma squared ti squared, etc. If we take the product of those two, that gives ti, and the product of 1 by 1, that gives 1. We sum, and we divide by sigma squared, so the K matrix, which is sometimes called, the K matrix is obtained by this formula, 1 over sigma squared, this thing here. If I continue, this is where I was before. I simplified the notation by saying the sum of the ti is the mean of the t. So t here is the x-axis values. They're assumed to be no. Those are the time instants at which we have measured our virus expansion data. So t bar is the sum of the ti multiplied by I, the number of data points. Similarly, I call st square the estimation of the standard deviation of the ti here, at least this estimate in 1 over I, such that the sum of the square is equal to st square plus t bar square, which leads to this formula here. And then the theorem says you take the inverse of this matrix, assuming it's invertible. If it's not invertible, then the theorem does not apply. So how do I compute the inverse? Well, this is a 2 by 2 matrix, so that's fairly easy. At the end, I obtain this matrix, k minus 1, which is sigma squared divided by I divided by S2 squares, and then those numbers here. And then the theorem says approximately the error, the estimation error we're making is jointly Gaussian with this covariance matrix. In particular, if I'm interested in finding a confidence interval for only one of the parameters, for example, alpha, I know that alpha minus alpha bar, which is the first coordinate of this error vector, is Gaussian with mean 0 and with variance given by the first diagonal term, which is sigma square over I st square. So that tells us the error of the first component and the error on the second component. And if we want, since we have the joint covariance, we see also that here in that case, we have a term for the cross covariance. And that can be used, for example, if we want an estimate not of A or alpha bar, but of any linear estimate of the two, for example. So that's a crucial matrix. Some numerical softwares like MATLAB give a name to that. They call it the variance covariance matrix. So they will compute it for you for the least square model that MATLAB supports. And the use of this is exactly that. That says how the error is distributed approximately. For example, if I said that this can be used for computing confidence intervals, assume I'm interested in the growth rate, alpha. What confidence interval am I able to derive for alpha having done this estimation here? I close the poll in 5 seconds. Closing now. And the majority says the second answer, which is the correct one. Well, the solution is in the previous slide. We have here that the alpha minus alpha bar, So again, alpha is unknown. Alpha bar is our estimate of alpha. We know it's approximately Gaussian with zero mean and this variance here. Well, that leads immediately to the formula. That with probability 95%, then we are within the 196 times the standard deviation. The standard deviation is sigma divided by square root of I st, which gives me a certain confidence interval. So that is how I could compute the confidence intervals for this model here. In passing, you see that the confidence interval decreases with square root of I, which is that, as expected, for many models that assume Gaussian dependency. But there are other interesting aspects. First, you see that we have closed form for everything when we fit a straight line. In fact, this exercise we did for this specific model can be done for any model, and we have obtained closed form that depends on things like st squared, right? Which is what st squared gives the variability of the x-axis values here, right? And we see that the larger it is, then the smaller the variance is. That means the more accurate the points are, which makes sense. If we have a cloud of points, but they're all centered around the same values, then the uncertainty about the slope will be much larger and about the model in general than if the clouds span smoothly the entire region. Right? So if there's a cluster of points in the middle, this is much less good for linear estimation. Voila. So the take-home message is there is a generic formula for computing confidence intervals with any least square model. In the case of linear least square model, this is also called linear regression, then we will see there are even simpler formulas. So linear here means linear with respect to the parameter here. So in general, we have fi of beta. The example we just saw is a linear model if we parameterize with log alpha, log a rather than a, right? So for such models, there is a closed form in matrix form. So I assume I have a model of this kind here. I still need to make some assumption for the theorem we saw before to apply. The assumption here is that X has full rank here. Full rank for X means that the model is identifiable, because if X doesn't have full rank, that means that there are multiple values of beta that will give the same output X beta. So X seen as a mapping is an injection. If this is not the case, of course, the parameter is not identifiable because there can be confusions between different values of beta. So that's a necessary assumption, but still needs to be verified. Also, like in the previous example, we know the matrix X. I use the notation X, which is often used in this literature, which is has nothing to do with the variables here. So the matrix X, which is also called the design matrix, is known. Like in the example before, I was assuming the times at which I'm observing the things is known in advance. If it's not known, we have a different type of model that we will not see in detail. So here is all the results we have for such a case here. We see that by the way, I forgot to ask Hossein, are we recording? I'm assuming we are. Yes, we are. Sorry for that. Back to this results. So from the model we have before, everything can be computed in closed form. So let me dive in particular to the first bullet here that I'm illustrating here. So this is the model here, I'm repeating, and how to solve the model. How to solve the model means how to compute for the beta hat. This is our estimate of the parameter. For this, it's usual to draw two spaces, the data space, this is the space in which the y value that we have are happening, and the parameter space, which is a space we don't observe, but where we can imagine that the parameter is residing. Since we have a linear model, this is a linear space for the parameter space. Then, for every value of the true but unknown parameter, there is an x of beta here, which is where the data point would be if there would be no noise. So that's the theoretical value of a data point. But the observable thing, which is the y with an arrow on it, the data, is not in this space. So I'm showing here a hypothetical case where the number of points capital I would be 3, so I can draw everything in 3D, and beta has dimension 2. So here, the space in which the x beta lives would be a plane in 3D space. But the data, of course, is not in the plane. It is anywhere because of the noise added to it. And then this theorem is simply computing the orthogonal projection of the data onto this space here. This is given by this formula, xk, where k is the matrix given in the theorem here. So we compute those matrices here, given by this quantity here. K is this matrix, where x is the design matrix. If x is full rank, we know that x transpose x must be invertible. That's one of the things that you can see as part of the theorem. Therefore, this is invertible. And this K matrix times X is sometimes what is called the hat matrix. This is the thing that transforms the data into the Y hat. Now, the Y hat is our estimate of where the true but unobservable thing would be if there would be no noise. And then, because X is a one-to-one mapping, is an injection, for every Y hat, there is a unique beta hat that we simply need to invert. Now, of course, inverting X is an injection, but not a bijection, so we need a better formula, and this is exactly what is given by this thing here. The beta hat is K, the matrix K, the same matrix, applied to Y here, and the hat matrix is, the Y hat is not given here. You have to find it. So this is easy, or at least in matrix form, simply because of the least, we use least square, because we have this assumption that all the noise terms have same variance, and then this is translated into a standard L2 problem, and we know that the point that minimizes the distance here, so what we're doing here is simply using the result we saw last week that says that the optimal point is obtained by minimizing the distance. Now, you may remember from geometry that the point on a linear space that minimizes distance is the orthogonal projection on this space here. And then the rest is how we compute orthogonal projections here. Here's an example. This is something that is perhaps reminiscent of your homework 1. Joe's shop has this behavior when there is a congestion collapse in its access point, and a simple way to model it, which is very often done in systems research when you want to predict or analyze things that are happening, then you do piecewise linear systems. Here, my simple model would be to say it increases until I reach the knee here, which is when congestion starts to occur, and then there is a collapse here. This is very approximate, but given the large uncertainty on the points, that's probably good enough, which corresponds to this formula. There is a knee here, psi, this point here, which is around 7 here, which is the point where this change occurs. And below this, so xi is the value on the x-axis. When x is below this, so this indicator function means 1 if the condition is true, 0 otherwise, we have this function, a plus bx. After that, we have c plus dx, so we have apparently so far 4 parameters, but in fact we have only 3 because we impose that the thing is continuous. So at the breakpoint psi, we have this constraint here. So in reality, we have 3 dimensions, A, B, C, D, A, B, C, or B, C, D. And if I'm assuming here that the noise is the same everywhere, which is perhaps a bit exaggerated, this is the model I have. Is this, by the way, a linear regression model? So what is called zeta is xi, in fact, but you all understood it's the same. I close the poll in a few seconds. Now we have a break even. The correct answer is yes, but only if we assume that the breakpoint xi is known. If it is known, then the function is given by this here. Since the points xi are known, then this is linear with respect to a, b, c, d. Right, so important thing to remember, the linear model means it's linear with respect to the unknown parameters that we're trying to estimate, which are here a, b, c, d. So obviously the dependency on a, b, c, d is linear. It's given by a linear formula with 0 coefficients for c and d when xi is below xi, and with 0 coefficients for a and b. So it is linear, it's a linear regression model. But if we assume that psi needs to be fitted as well, then it is a nonlinear model. So because it is linear, we can fit it using the formulas here. So here I think the x-axis units are a bit different. Assuming here the breakpoint is 70, so I took an arbitrary decision, decided the breakpoint is at 70, then I can fit the 4 parameters with, but only 4 are dependent. So when I do the fitting exercise, of course, if I want to use MATLAB or NumPy, I cannot give 4 parameters because I will not have a full rank matrix, right? I need to add the constraint that a plus 70b, 70a plus b is equal to 70c plus d in this specific case, and I need to somehow reparameterize my system, for example, by deleting d and saying that d is a linear combination of a, b, c. Then I can obtain 95 confidence intervals for ABC using the formulas we just saw before. And for D, well, D is a linear combination of ABC, so I can use the variance covariance matrix to obtain the confidence interval for D here. So this is exactly what it will give us here. And perhaps the thing of interest that we're interested in is the slopes. So I said the slope is CD, the slope is in reality, the slope is in reality D, right? Whoops. Here we are. What I'm interested in is there congestion collapse, for example? So the slope of this part, which is given by this thing here, we see that it's negative with a fairly large uncertainty, but still much larger than the value itself. So there is really a negative part here. At least if we believe in the breakpoint being 70, this is what this will give us. We should also verify the residuals. Here I plotted the residuals, which the dots here, and I did a QQ plot, and we see, well, it's not exactly normal. We see there's a trend. Here it's below, here it's above. So it's approximately normal. It's not a violent one, but probably the model can be improved a bit, which corresponds to what we saw also on the figure. We saw that on the left, the error terms are a bit smaller. So perhaps an error term that would increase with the value would make more sense. But let's stay with that here. Now, that was the easy part, the linear case. Very important because it has closed form formulas with matrix expressions for the projection matrices that are easy to compute numerically because everything is based on matrices that are semi-definite positive. So everything, including the inverse, will be easy to compute. So this is why it's used even for large models. However, there are cases where not everything is linear. So when not everything is linear, we have this additional point here that we can use from the previous result. Let's see how we can use it in our example here. The nonlinear part is, of course, the determination of the breakpoint psi here, because our model, our true model here, doesn't give us the value of xi. There's no reason to believe that the value of xi is 70 rather than something else. We will see that, in fact, the best estimate is not 70, but the confidence interval is between 73 and 80 at level 95%. So my rough estimate of 70 was a bit off here. How can I get the maximum likelihood estimate of xi? Well, here it's very easy, but that's a very generic method that's important when you have large models that you need to fit, in particular in many data science models. We have a model which is almost linear in the sense that everything is linear except the dependency on xi. So we have a model that has parameters. Here I parameterize with ABD. Remember that one of the four ABCD depends on the others when xi is known, so we should remove it. So here I parameterized using ABD and xi here. And if xi is known, this is a linear regression model. So we can capitalize on this fact to separate the variables and do an optimization in two parts. First, for every xi, if xi is fixed, I can easily solve this optimization problem. Remember, this optimization problem is the likelihood. Here, the likelihood is is given by the PDF here. Then for every value of xi, I can easily solve the optimization problem. This is given by a projection matrix. So, and I can compute the corresponding value of A, B, D, and sigma. And if I take, in fact, not the likelihood, but the log of the likelihood, for tractability here, but also for other reasons that we will see next, the problem becomes finding the max of overall parameters is the same as finding the max of this max when xi is fixed here. Here I'm using a property that maximization is associative. If I want to find the max of many things, I can first take the max over ABD sigma, and then I have only xi as a degree of freedom, then I can take the max of this. This works when we have max of max. When we have mean of max, that doesn't work here. So the problem we have is to now find the maximum of this log likelihood, optimal log likelihood, when xi is the only thing that is not fixed, that is not optimized upon. This has a name, it's called the profiled log likelihood. P stands for profile here, that's the word that statisticians use. So now we have to maximize over xi. Now this is completely nonlinear, but maximizing over something nonlinear might be complicated, but except if it's in low dimensions. Here, I have only one dimension. So how do I maximize? I can do brute force things by plotting this function, PLI of xi, which is what I did here. So here, for every value of xi, I do what I did a minute ago. A minute ago, I said xi is equal to 70, and let me solve the problem. So I solved the problem and computed the likelihood. You remember from last week that we saw that least square problem have the property that we also know how to solve the optimization problem, but we know also how to get the optimal likelihood from the optimization problem. And MATLAB or NumPy will return it. So I have this value, and for every value of xi, I plot it. So on the y-axis, I have the likelihood. I do it for here values with an accuracy of one, a quantization of 1. So I did it for values 10, 11, 12, etc. And I get this curve here. Now, what is the maximum likelihood estimate of xi? Well, it is the value that reaches the maximum. Here I find 77. Of course, with some uncertainty, because I've quantized here y units of 1, but that gives me still a better value than what I had before. So the point that gives the maximum here is exactly the maximum likelihood. And the value of A, B, C, D that corresponds to this xi are the joint solution to the global optimization problem. So that is fairly simple. The nice, sophisticated additional trick is this one here. There is a theorem that says that if we consider if we do the following, we plot the value that achieves the maximum. This is psi hat, that's the maximum likelihood estimate of psi. Then there's a magic number, 192.07 at probability 95%. That comes from the chi-square 1 distribution. Here p is equal to 1. And the theorem says that with probability 95%, the true value of psi will be in the interval that is obtained implicitly by taking the profile log likelihood between the maximum and the maximum minus this value here. So I go to the y-axis. Here I have the maximum. I go below the maximum by reducing by this magic number, 192.07, which comes again from the tail of the chi-square distribution. It depends on of course, on the confidence level. If I have 0.99 confidence level, the interval will be larger. So I have on the y-axis this interval, and then I need to find the corresponding value of the x-axis that are within this interval. I need to do it numerically, which is what I did here, and that gives me a confidence interval 73.80. So this is what this theorem will give us. Here in the appendix of the lecture notes, you have the complete story. Here in the main part of the lecture note, you have the story in this specific form of this system here, if I want to give a confidence interval with respect to one of the parameters of a regression model. So take home message, well, we can, if we have a least square model where all parameters except the small numbers give a linear dependency, then there's a good chance that we're able to solve everything in quasi-closed form and with confidence intervals. So, of course, this is beautiful, and this is why least square is used so much. So in practice, in many practical cases, we will use least square because that's the most efficient we have, and we don't have infinite time to do something else. But there is another method that you must know, because when it's applicable, it's way better. And it has to do with a different model of the noise, which would have an exponential distribution. Least square methods corresponds to assuming that the noise, the error terms, are Gaussian, which is sometimes true, is very often true, but is not always true. And in particular, the Gaussian distribution has the property that its tail decays very, very fast. We know that the probability that we are larger than 6 sigma, for example, is astronomically small, 0.9 4 zeros before, and followed by a 1 approximately. Which is also why we use Gaussian distribution for things, for example, that have a finite support. Even a positive random variable, we can model it as Gaussian, even though in theory, the Gaussian distribution takes all positive and negative values, but in practice, it does not. In practice, it decays very, very fast. Why is it important to decay very, very fast? Well, if you're confident about your measurement system, and you're confident that the errors are truly bounded in some sense, then Gaussian model is good. If you're less sure, in particular, if there are values that diverge a lot from the other values, and you don't really know whether they are outliers or whether they are truly correct values, then this Gaussian assumption might hit you, because with the Gaussian assumption, the only way you could have something that is very, very different from other values is that the noise model has a huge variance here, which might not be the case. It might be that there are just 1 or 2 points that are off here. So one classical method to address such cases is to use the Laplace distribution for the noise. So what is the Laplace distribution? Well, the Laplace distribution is constructed as follows. We start from the exponential distribution. The exponential distribution is given by this PDF. The probability, the density of value x is exponential minus lambda x, only for non-negative values of x, and lambda is the normalizing constant here. And it's also well known for this CDF. 1 minus the CDF is exponential minus lambda c, or the CDF is 1 minus exponential minus lambda c. So the probability that the random exponential variable is larger than c is exponential minus lambda c. Something easy to remember. So that goes exponentially fast to 0, but this is way less fast than for Gaussian, where a Gaussian is approximately in lambda c squared, in some quantity c squared here for the tail distribution. Not exactly, but approximately. So that is for the exponential distribution. We spoke about it in another context. When we spoke of queuing theory, for example, we said that the exponential distribution has this nice property of being memoryless, which we will come back to it when we talk about model fitting, about memoryless and heavy tail model. Here, memoryless is not the property we're interested in. What we're interested in is that, one, it's tractable, and second, it decays much less fast than the Gaussian variable. Exponential distribution is always producing something positive. It's used, for example, for producing inter-arrival times. Out of this, so it's not a noise model. Out of this, we make a noise model as follows by saying, I draw a random variable from the exponential distribution. With probability 50%, this is my output. And with probability 50%, I take the opposite of that, -1. The resulting thing is called Laplace noise. So this is the topic of this second part. So, small question, small probability exercise. What is the PDF of Laplace noise? I close the poll in a few seconds. And the majority says B, which is the correct answer. Still, it's interesting to know how we solve such a problem. Let me show two methods, one which is heuristic, one that is exact. I think it's important to know both here. So let Q equal 1 when we choose the first alternative, when we output Y, and Q equals 0 when we output -Y. Well, the PDF, we can interpret the PDF as giving the probability that the random variable is equal to x plus or minus dx here. So what is the probability that we fall in this interval, right? Well, it depends. When x is positive, the probability that capital X falls in this interval is, so if x is positive, and this heuristic method assumes that dx is small enough so that this interval is entirely positive. So if we fall in this positive interval, that means we drew q equal 1, which occur with probability 1/2. And then what is the probability that given that q is equal 1, we fall in this interval? Well, it's the probability that the exponential random variable from which x is constructed falls in this interval. So the event, x is in this interval, is equal to the conjunction of those two events. Q and Y are drawn independently, so the probability of the end is the product. 1/2, what's the probability of this? Well, approximately it's lambda exponential minus lambda x dx. That's the interpretation of a PDF. If we want to be accurate, the probability is plus other terms that vanish in front of dx. So this little o of dx, that means that this is dx multiplied by some quantity that goes to 0 when x goes to 0. So at least heuristically, that tells us that when x is positive, this is the PDF. And conversely, when x is negative, we find a similar thing where we need to replace x by minus x or by the absolute value of x. So when x is negative, that's the value we find. So in both cases, we find this because here x is absolute value of x, and you still need to handle x equal to 0, but let's leave it aside. That's one way to get the answer, which is interesting because it's intuitive. Another way, which is rigorous, is to compute the PDF, is based on the observation that what is a PDF? Well, a PDF, interpretation one, is this one. The probability that x is in a small interval is equal to the PDF times dx. Right, that's first interpretation, physics interpretation, which is good enough for most cases. If you are worried that it's not rigorous, here's the mathematics interpretation. The PDF is obtained by the following. If I give you a test function, which must be integrable or it must have good properties so that all those formulas make sense, but other than that, it can be anything. If I give you an arbitrary test function, the expectation of phi of x is equal to the integral over the whole scope of this random variable, which is here a real random variable, so from minus infinity to plus infinity, of the test function multiplied by the PDF. So that's another way of defining the PDF. In fact, that's the distribution way. That's a way that is more powerful because that still continues to make sense if fx is a Dirac or weird things like this here. So the first thing to remember is that if I am able to write this for any arbitrary function phi, that completely defines the PDF here. In fact, if we take for phi exponential, a complex exponential, we obtain the Fourier transform of the PDF, which is called the characteristic function. If we take a negative exponential, we obtain the Laplace transform, etc. We can take a number of test functions. If we take for phi the indicator function from minus infinity to plus c, this integral is the probability that the random variable is less than c. So this is the CDF here. So depending on what phi we give, we obtain different things, and all of these different things uniquely characterize the distribution. So of course, if I let phi be anything, that uniquely characterizes the distribution, therefore, it should uniquely characterize the PDF here. So let's do that here. I compute the exponential of phi of x for an arbitrary phi, and for that, I condition upon the binary flip toss of a coin that I did before. Exponential, given that q is equal to 1, then x is in fact an exponential random variable. So this conditional expectation is equal to this formula for exponential random variable, which is the same as that because here x is positive, so absolute value is positive. Now, given that q is 0, so I've returned the decision to go negative, x is equal to minus y. So I apply the same formula here. What is the expectation of phi of minus y? Well, this is a function of y, phi of minus x. So it's the integral of phi of minus x given by the PDF of the exponential variable. I do a change of variable, change x into minus x, and the usual rules of change of variables in the integral will give me this thing here, which is the same as that because x is equal to minus absolute value of x. So I have obtained the conditional answers, I've obtained the conditional distribution here. Now I need to find the unconditional distribution, and I will say I need to take 1/2 of this, multiply by the probability of this, which gives the 1/2 here. So it will give me 1/2 of this plus 1/2 of that, which gives the correct PDF here. So this is a plot in red of this Laplace distribution here. I chose two distributions that have the same variance here, the Laplace one, and here the Gaussian with unit variance, and this one with unit variance. The variance is 2 over lambda square. So if I want variance 1, I have lambda equals square root 2. So in terms of PDF, we see that's something that decays much more slowly to zero compared to Gaussian. And we see that also in the 1 minus CDF. So that's the probability that the error term is larger than some threshold X in log scale on the y-axis. We see that it decays very fast for the Gaussian. And of course, it's a straight line for the Laplace noise. So we have seen what Laplace noise is, and we understand also from these curves that it's meant to model the fact that values that are very large are not that unlikely. So what remains to be seen is how we can fit a model with Laplace noise. So the model is similar to what we had before, except now we're assuming the noise terms are IID with Laplace distribution. Then, as you might have guessed, this corresponds exactly to a score function, which is equal to the absolute values here. So the L1 norm, if I take as error score the absolute value of yi minus fi of beta, summed over all data points, and I have what is sometimes called the L1 norm of the difference between the data point and the theoretical point here. And the value that minimizes this is exactly the maximum likelihood estimator of the parameter beta. And lambda is given by 1 over lambda hat is 1 over I, the error term that is here. So in other words, the signal processing method that takes L1 score corresponds exactly to Laplace noise here. So this is what we saw just now, assuming that the noise is IID Laplace corresponds exactly to taking as score the L1 norm of the error terms. Here, same problem as with the least square. When we do that, we assume something called homoscedasticity. We assume that the variance is the same for all error terms, even if the formula for the variance is different, but here it's the same. If you have some reasons to believe it is different, then you should put some weights onto the variance, which will correspond to weighting the error term here. Here the weight comes as multiplication to lambda, whereas here it came as division to the standard deviation. This is because the parameter of a Laplace transform of a Laplace distribution is in inverse of the values. For the virus propagation example that we saw before, I'm showing here two lines that look quasi the same, the red and the green. The red is dotted, the green is plain line here, and the blue points are the values that we had. Whether I fit L1 or L2 gives quasi the same. Not exactly, but quasi the same. So that's the good news. Essentially, we are never too sure which error model is fine, but here we see that both give the same. Except, of course, if there are outliers. So here I'm taking my original data set and I add artificially another value here, which is a complete outlier. It's a huge value for one data point here. And we see what happens now to the least square and L1 estimation here. We see that the least square line becomes very different, whereas the L1 line is affected, but in some sense ignores the very large value. So the least square is trying to minimize the square of this error, so is forced to bring the line up. If we redo the optimization numerically, we find on this line the original values, then the corrupted values. We see that in the second case, the values of the rate is slightly different now, but the difference in the least square is considerable. And if we use this to do a prediction 6 hours in advance, we see that the impact on the prediction is indeed significant, but is very small when we do L1 norm minimization as opposed to least square, where here the impact is dramatic. So that's exactly the take-home message. If we do least square, we are susceptible to outliers. If one value is very outside the set that we have, this is probably an error, right? So if we have an error here, then of course our thing is wrong. But the embarrassing thing is if we do least square, outliers do matter. So if you use least square, you need to have screening for what is called bad data detection. You need to have a way to eliminate them. Here it would be easy by screening the data if you find there's no reason that it jumps in such a sudden way. There are systematic methods that you can easily imagine. For example, a systematic method to eliminate bad data detection consists in doing the estimation, like we did here, the green line here, then examine the residuals, so the error terms that are estimated, and eliminate the residuals that are extremely large. For example, here we would find a very large residual, and we would eliminate it. When we eliminate it, we would do this regression. But this is, of course, heuristic and is not necessarily always optimal. So it's better if we can afford, if we have the choice between two, by doing L1 instead of least square, then we're much less susceptible to the outliers. So we can even, in many cases, ignore the outliers. To understand, in fact, why we can ignore the outliers when we do L1 norm minimization, let's look at this very simple example that will give us all the important features. So this very simple example is a revisitation of what we did a few weeks ago, which is to estimate a confidence interval for the mean. When we model a data with the mean, that means we say the data is equal to a constant plus noise. That's one way of seeing this. Although we're not saying M is the mean, but we say we can summarize all the data by saying all the data have a common value and the difference is due to error term. So assume that's my model. I have capital I data points, yi, and I want to estimate M. If I do least square, or if I do L1 norm minimization, I will have those two methods. The first method corresponds to saying that Y is the model plus noise. The noise is Gaussian. In the other case here, if we do L1 norm minimization, we will say Y is M plus Laplace noise. How do we compute those values here? So if we use the first case, if we assume the noise is IID Gaussian, we will do least square fit, right? What is the least square fit of this model? That's the question for you now. I close the poll in a few seconds. Closing. And the majority gives the third answer, which is incorrect. The correct answer is answer B. Let us see why. Well, there's a very simple way to look at it. The least square fit, as we know, minimizes the L2 norm of the errors according to the model. So the model says every y should be equal to m. So if yi is not equal to m, here this is the error that we have, yi minus m squared. So we minimize the sum of all this here. Now you may know or you don't know, but if you don't know, now you do. This formula here, which says that the sum of yi minus m squared is the sum of yi minus the mean of y plus I is the number of data points, times m minus y bar. Right? This is a formula that is used, for example, to explain that the variance of a random variable is equal to the expectation of the square minus the, we can, if we divide by y, this gives the variance. And here we have no, I'm not sure what the formula comes from, but this is a well-known formula that you can expand by simply expanding the squares here. So this is something that's independent of m here, and we want to minimize over m. So what is the value of m that minimizes that stuff? Well, it is the value that minimizes this, and this is when m is equal to y bar. Okay, that's a simple but smart solution. Instead of being smart, we can be systematic, which is even better. So we can use a theorem because we know that for a linear regression model, there's a closed form. So this is linear. Here, the parameter is m, and the dependency on m is linear. It's equal to m, which is the simplest linear formulation. So if we map this to our general theorem, we need to write what is the design matrix X. So we need to write yi is equal to a matrix times the parameter. Now the parameter is only one m. So here is the matrix explanation of this model here. The vector, the column vector of all the y is equal to a column vector of ones times m plus epsilon. This is a vector of epsilons here. So this is this model here. So I applied the textbook solution. I need to compute x transpose x and this K matrix. So x transpose x, so x is this column matrix, gives me this. So it's a 1 by 1 matrix, which is a number. It's I, the number of coordinates, capital I. The K matrix that we obtain here, we take the inverse of x transpose x, which is 1 over I, times this matrix X transpose, that gives me this here. This is my K matrix. And therefore, M hat is equal to the K matrix applied to the data point. This is this formula here. Therefore, if I apply this matrix, which is a vector of 1, to this column vector here, that gives me Y bar. So that's another way of getting the estimate. A very complicated way, but that's reassuring. It shows how the general method works. So we have seen what the least square model gives. What does the L1 minimization model give? So I have the same model, same thing, but I assume now that the noise is Laplace, therefore I do L1 fit. What will I get? I close the poll in a few seconds, in 5 seconds. Closing. And there is a tie between the sample mean and the median. If it's the sample mean, that would mean that L1 is equal to L2. The correct answer is it happens to be the median. Why is that? Well, it's a bit more complicated, but it's instructive to see why. For L1 fit, the function to be minimized is this one, sum of the absolute value yi minus m. So to see what it is, I draw this curve. So for every value of m, I draw this quantity, which is a function of m here. Now, what is it? Well, it gives me exactly this red curve here. You see that, for example, when m is between y1, what is y1? That's the order statistic of the smallest of the y. When m is larger than the smallest, but also is larger than the smallest, but smaller than the second, what is f of m? Well, it depends on the sign of this. So that gives m minus y1, y2, etc. So that's a linear function. So between those two values, it's linear. And the slope is equal to the number of plus signs minus the number of minus signs, since there are here 1 and 4, that gives -3 here. So in general, we see that the derivative, so we have a piecewise and continuous linear function. This is continuous, the absolute value is continuous. That has a derivative everywhere, except at the points where we hit exactly some of the y values. And the derivative is equal to the number of points that are below m minus the number of points that are above m. Right? So when n is odd, f decreases when m is less than the median, and f increases when m is larger than the median. Therefore, the absolute minimum is at the median, which is what I did here. When the number of points is 5, we see that the minimum is exactly at 3 here. Now, if the number of points would be even, if it would be 4, there would be a flat line here. So there would be a minimum value that's reached over a whole interval, but it would be reached also at the median, which, if you remember, by convention is the middle of this interval here. So in summary, what we have obtained is that the solution to this optimization problem is the median here. So what is the answer to these two problems? If we solve in least square, we obtain the mean. If we solve in L1, we obtain the median. Now we know from direct analysis of median versus mean that the median is more robust. It's easier to compute a confidence interval. Not it's easier, but the validity of a confidence interval and of the estimate is better when we have L1 norm minimization. So it's the same here. When we do L1 regression model, we expect to have something that is more robust to such assumptions here. Now, the question that remains is, but does it work? I mean, how can I do numerically linear such a regression here? Well, it is less simple, but in the linear case, it is completely tractable. So if I consider again the linear case, it's like before, we have linear is the dependency with respect to the parameter, and the noise here is assumed to be Laplace here. Then what we know that what we have to do is to minimize this quantity here. And in order to minimize this, well, this is a nonlinear problem, but it can be transformed into a linear problem by adding supplementary variables that are the values of these absolute values here. If I call them ui, I have to minimize the sum of the ui subject to ui being larger than the absolute value, which is equivalent to being larger than this and the opposite of this. Why is that? Well, in the quiz, you will have more steps to go through that in more detail. But that's the important part. That means that if the dependency on the parameter is linear, then we have linearized everything and those constraints become linear. Therefore, we have a linear optimization problem, which, as you may know, is the most tractable of the optimization problem. So in practice, that's also easy to do here. So if I apply this, for example, for the congestion collapse model I wanted to bring before, if I take the assumption of Laplace noise here, I can, for every value of psi, I can also compute, solve this linear program and obtain the values of the parameters here. And then I can find the optimal value of psi by, like we did before, computing the profile log likelihood and finding the one that finds the smallest the largest profile log likelihood, or minus the smallest score. And the one that finds the smallest score is here, you see, is much less uncertain. It's somewhere between 65 and 75 here. So that's one way to obtain, to solve the problem. Like in the least square case, here I capitalize on the fact that when psi is fixed, I have linear regression. And to find psi, I resort to numerical optimization here. When I look at the residuals, I estimate the residuals from the model, and I do a QQ plot. Now, of course, it's not a normal QQ plot. It's a Laplace QQ plot. So I plot the quantiles of the residuals versus the theoretical quantiles of a Laplace distribution, which are easy to compute because Laplace as a closed form for the CDF, we obtain this thing here. So we see this thing here shows some perhaps deviation, but it's not clear that there is a strict deviation. So accepting the idea that the noise is Laplace is stronger here than for the Gaussian case here. The bad news about L1 norm minimization is that there is no closed form for the confidence intervals. So we need to work a bit more to obtain confidence intervals. Here I obtain them. We see slightly different values from in the least linear regression case. And the next topic will be, how do I compute these confidence intervals? Here, that's an opportunity to see a radically different method, which is, I would say, the last resort method. When we're really stuck, but we have a computer, then we can replace sophisticated statistical computations by simulations. And the specific form of simulation is the bootstrap. We have seen that already. We have seen that with Monte Carlo simulation, we can compute, for example, an integral by simply interpreting the integral of the expectation of a random variable and then generated 1 million samples of this random variable and compute the sample average of what we have. So it's the same idea here, the bootstrap, except here, as you will see, we use residuals. So here is how it works. Assume we have a parametric model with parameter beta, so beta is a vector, and lambda is our noise model for the Laplace noise. And we want to find a confidence interval, for example, for one coordinate of beta. I know how to estimate beta 1 by solving a linear problem, beta, and not just beta 1, but all beta. So let beta 1 be our estimator of beta 1. Of course, that's a random thing. We have obtained it for a given set of data that we have. But in the rest, in the bootstrap method, we will treat it as something fixed here. However, what we want to compute is a confidence interval. So it's a function u and v of the data such that the probability that the true value is in this interval is at least larger than, for example, 95%. This probability, I put here an index beta lambda because it depends on beta and lambda here. So assume someone tells us the true value of beta and lambda. Then in theory, we can compute the quantize of the distribution of beta 1 here, right? If I know beta and lambda, since beta 1 is obtained from the data, I can obtain its distribution here. And let me call u and v the quantize that I obtain of beta 1 hat when the true parameter beta and lambda are given. How can I obtain the quantize? Well, for example, I can do simulation. If you give me the true beta and lambda, I can simply simulate artificial data points of my model. I do 1 million simulation runs. I solve for each of my simulation run, I solve the linear program that gives me an estimate of beta 1 hat. And that gives me 1 million samples of beta 1 hat, given that beta and lambda have these values here. And then I can estimate the quantiles of this distribution. Out of my 1 million points, I eliminate 2.5% top and bottom values, and that gives me my lower and upper bound here. So in theory, we could do that, except of course, the problem here is we don't have beta and lambda. So how do I do? Well, I don't have beta and lambda. The bootstrap idea is to replace beta and lambda by the values that we have estimated. So I take the beta hat and the lambda hat, and I redo simulations, and I compute the distribution of the simulated output, and the 95 coverage interval gives me the confidence interval here. So that gives the following algorithm, right? If I know beta and lambda, I do capital R time, simulate points from the model, and the model is the model that is here, right? This is the model. Beta is known in this hypothetical exercise. Epsilon is what I simulate from the Laplace distribution. So I can generate capital I data points, and I can do that 1 million times. Each of these 1 million times is called a replay experiment. So I replay the experiment capital R time, and I look at the quantiles of the 1 million estimates of beta hat here. This is what we should do in theory. What I will do, as I said, is by taking the values of the parameters, the ones that I've estimated. This is called the bootstrap, or more exactly, the parametric bootstrap. It's parametric because we use the parameters that we've estimated. And bootstrap is the word that for some reason means we simulate. So it's a Monte Carlo simulation of the model using the parameters that are estimated from the data that we have. So for the example that is here, I had find lambda hat is this value here. So I draw capital I residuals from the Laplace transform. I simulated capital I artificial data points. So I did 999 simulations of the blue cloud, and I looked at the estimates that I had for A, B, C, D. And then I took the 25th and 95th, and this gave me this confidence interval for D, which is the parameter of interest, which is the rate of collapse here of my system. So this is one method. It seems a bit magical. There is a theory that says when it works and when not. Of course, if the number of data points is very small, it's a bit risky because the estimation that we have is not so large, but at least it gives one method with reasonable results most of the time. What I showed was the parametric bootstrap. There is an even more radical way, which is very efficient and very simple to use, which consists in doing the following. When we want to do replay experiments, the idea is to generate the noise terms, epsilon here. We did it in the parametric bootstrap, by drawing from Laplace lambda here. But instead of drawing from Laplace lambda, we can resample from the residuals. Resample from the residuals means I estimate my model and I estimate the residuals. The residuals is what I've shown here, for example. Those are those values here. So I have capital I values. Each of those points is one residual. Now, if I believe in my model, that is, I believe that the original model was assuming that the epsilons are IID, I have capital I samples that are of my unknown residuals here. So if I want to simulate the model again and again, one method consists in saying, well, I will put those capital I residuals into a box and I will draw them from this box by putting with replacement, and that gives the following algorithms. So I have, so capital R is 999 or 1 million, depending on the confidence level you want to have. I have computed my residuals. I call them E here. Those are the blue points I showed before. And for every replay experiment, I draw I of them with replacement. Why with replacement? Because we want to model something that is IID. So IID means with replacements. If I've chosen the first value E1, I put it into the box again. If I don't do that, then they are not IID. If I don't do that, the last value is entirely determined by the previous ones, for example. So we need to do it with replacement. And then I generate, so I call that capital E for replay experiment R, and I generate a replay experiment by taking this. So this is in fact one of the residuals I have, but perhaps not the one that corresponds to the index I. Most of the time, not the one that corresponds to index I. So it gives me this replay experiment. I re-estimate beta using this replay experiment, and otherwise I do like before. I sort, and the 25th and 975, when capital R is 999, gives me my 95% coverage interval of my unknown parameter. So you see, it's quite simple-minded, and most of the time it works well. Here I did it for this example here with the 4 parameters we want to estimate, with the 2 methods, with the parametric bootstrap and with 999 replays here. Here there must be a typo somewhere. It's not 149. The values should be similar. And here we find small differences. So of course, the values that you obtain with it should not expect that. In particular, the confidence intervals should not be taken as very solid, but they are second order quantities. So we can still use that as a simple solution to find the confidence interval here. You see that the two methods will give slightly different values for the slope, but essentially the same diagnostic. The slope is negative with some uncertainty, which is large about it. Large, but still leading to negative value here. So the bootstrap is used typically when we need to do confidence intervals, for example, or predictions also when we need to do prediction or confidence intervals and we are really stuck. So the idea is to use, if we think about it, the data itself as estimate of the unknown distribution of the data. In one case, we use the data to estimate the parameter lambda, for example, and then we pretend it's the true one. In a more extreme case, we don't even use the distribution, but we use the sample values of the residuals as a proxy for the distribution here. For example, if we would not know the formula for the confidence interval for the mean, if we apply this method, of course, nobody does that, but as a thought experiment, it's a good idea to do it once in your life. Assume you want to compute the confidence interval for the mean of a data set yi. So the model is y is identically distributed from some distribution f, and the problem is to estimate the mean of f. We don't know f, but we want to say something about the mean. What do we do? Well, with the bootstrap from residuals, the residuals are the y's themselves here, we replace the unknown distribution f by the data itself. So the mean of f is the sample mean of the distribution, and the distribution that we've taken as a replacement for f is the distribution that puts probability the same at all the points yi. So we've replaced the true CDF by the sample CDF here. If we want to do this, which of those two algorithms would be a correct implementation of the bootstrap for a 95% confidence interval of the mean? I close the poll in a few seconds. And the majority says A, which is the correct answer. In fact, A is doing exactly that. So we draw one integer uniformly between y and I. So this unif also, of course, means to be taken with the constraint that is an integer. So we've seen how to sample such a thing. With probability 1 over I, you get any of those values here. And then we pick the value with index capital K, which is taking one of them randomly. And since we do it again and again, it is with replacement, so value can be taken several times. This one corresponds to sampling n objects again, but without replacement, because we draw a random permutation. How you draw a random permutation is another story, but there are boxed functions that will do it for you. Here it is with replacement, so that will be incorrect. That will in fact generate less variability than this one. So this one is to be preferred. That's the correct implementation of the bootstrap. Just for fun, I did it for this example that we had here. Here I have two data sets, and we had seen how to compute confidence interval using various methods. One assuming the data is normal, the other one, which is perhaps suspicious here, but the other one, which is the classic method, assuming n is large and the variance is finite, which is a classical formula we have for confidence interval for the mean. And another one here, which is obtained by doing the bootstrap, and we see that they give all the same confidence interval, which is a reassuring result, which is in the good cases, in particular when the data is not wild, is not heavy tail, like this one here, all the methods will give quasi the same confidence intervals, which speaks also in favor of the bootstrap here. Voila, with a few minutes ahead of time, we come to a conclusion of this part. So in summary, the statistical method for fitting a model requires modeling the noise, which is good and bad. It makes the things more complicated, but also it gives you an argument to decide one or the other in favor of one of the other methods. And in particular, the most important things that needs to be screened is whether the almost cadastic model makes sense. So least square fitting is okay, it's the simplest, but if we assume that the noise has same variance everywhere, that's, but we must assume that the noise has same variance everywhere, and that's easy to verify if we think about modeling the noise here. Least square fits corresponds to Gaussian noise, L1 fit corresponds to Laplace noise, and we have seen that in many cases, in fact, least square is trying to integrate the minimum distance, so it does things like integration that corresponds to small. It tries to find things that correspond to means of some quantity, whereas L1 will try to find something that corresponds to median of some quantity, putting as many points on the left as on the right. Now we understand why it's more robust, right? If a few points are outliers, L1 might, those points that should be in the middle and are far, okay, that will change a bit the L1 estimate, but the fact that they are very, very far from the middle will not affect L1, because L1 simply counts how many points are larger than another one here. So this is where the robustness comes from. And then we have done our first use of the bootstrap, something that we will use again, because that's very convenient, in particular for forecasting. When we don't know how to compute things that would otherwise be complicated, then this is recycling the idea of Monte Carlo simulation, combined by the confusion, assuming that the estimation of the parameters leads to something that's close enough to the correct values. Voila, that's all for today. I encourage you to do the quiz. The quiz on this part is a bit longer than the quiz on the other parts, because now we start really going to the meat of things. Now we need to do some statistics, some computation, some things that are perhaps a little bit more mathematical than what we did before. So I encourage you to devote a bit of time to the quiz. Hopefully the lab will be less long for everyone than lab 2 was. Thank you very much. Enjoy the quiz and the labs. And as usual, we are online for answering your questions.